Namaste everyone, welcome to class 11, chapter 4 mathematical induction. In module 2, we learned steps of mathematical induction. We proved mathematical statements involving some of the terms and we proved mathematical statements involving product of the terms and some rational terms. In this module 3, we shall cover more examples on principle of mathematical induction involving inequalities and divisibility problems. Before that, we will recall principle of mathematical induction steps. Let us see, for a given exam statement Pn involving natural number n such that P1 is true, this is the basic step we need to do. Then we assume the given statement Pn is true for n is equal to k. Then if the statement Pn is true for n is equal to k, where k is some positive integer, then the statement is also true for n is equal to k plus 1. Once the truth of Pk is established, that implies the truth of Pk plus 1, and after doing these steps, we can easily conclude that Pn is true for all natural numbers. Let us understand with the help of this example. Here, this is the question number 12 of exercise 4.1. Prove using principle of mathematical induction. This is the statement here. This is the sum of GP A plus AR square plus dash 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 plus AR to the power n minus 1. This is sum of GP of n terms, which is given to be A into R to the power n minus 1 divided by R minus 1. As the first step, we first define the statement as Pn, the same statement given above to be proved. We have defined it, taken it as Pn. Then we will verify it for 1, P1 left hand side. Left hand side means we need to take first step or first term of our this Pn, that is A, and for right hand side what we are to do, we have to replace this n by 1. After replacing this n by 1, we got r minus 1 in the numerator and r minus 1 in the denominator, both get cancelled. What we are left? We are left with A only. So, left hand side and right hand side both are equal. We can easily conclude that P1 is true. Once P1 is true, now the door is open for the next step. What we have to do is, we have to assume that Pk is true. And what is Pk? Here the Pk is the same statement with a little change. In place of n, we are required to replace this with k, and this becomes A plus AR square plus dash 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 AR k minus 1, that is equal to A into R to power k minus 1 divided by R minus 1, and we will take this statement as equation number 1 that we will be using further. Now we need to show that Pk plus 1 is true whenever Pk is true, because we assume that Pk is true and we need to establish that whenever Pk is true, Pk plus 1 is also true. What is Pk plus 1? Pk plus 1 is A plus AR square plus AR k plus AR to the power k plus 1. Wherever there is a k, we replace it by k plus 1. Since here it was k minus 1, this becomes k plus 1 minus 1, which is equal to A into R to the power k plus 1 minus 1 divided by R minus 1. This is the statement which is to be proved. Now we have rewritten this statement because we need it to prove further. The left hand side is to be equal to right hand side. We have to make it, we have to prove this. First the step is, while proving Pk plus 1, we take left hand side. What is left hand side? Left hand side till k plus 1th term. This is k plus 1th term. What is its previous term? Its previous term is AR k minus 1, just previous to this. and this is nothing but, this was equation number 1, which is Pk. From Pk expression we can replace this entire term like this. This is Pk, and after solving k plus 1th term we get ar to the power k, and here we have replaced this term Pk by this expression from equation 1, a into r to power k plus 1 minus 1 divided by r minus 1, and this is nothing but this term written again, which is k plus 1th term, and this was the result of kth term. After solving this by taking LCM, we have taken LCM r minus 1, that got multiplied with this term. And while we open these terms, a into r power k minus a, here also ar power k into r, ar power k into minus 1, this is the same. Now in these terms you can easily observe that this term a into r power k and minus a into r power k are being repeated but with the opposite sign. So these two terms can be easily cancelled out. Let us see here, this term and this term both cancelled. What we are left with? We are left with minus a plus a power r power k plus 1 divided by r minus 1. We can rearrange these terms, writing positive term first and then minus a. Now in this expression we can take a common in the numerator. After taking a common, we are left with r to power k plus 1 minus 1, and this is nothing but right hand side of Pk plus 1, which we wanted to prove. So we can say that Pk plus 1 is true whenever Pk is true. So to prove Pk plus 1, the truth of Pk plus 1, we need to prove or we need to assume that Pk is true. Hence, Pn is true for all n belonging to natural numbers. Now we move on to another example. This is an example 6 of your chapter 4, where we need to prove that this expression, which is 2 into 7 to power n plus 3 into 5 to power n minus 5, is divisible by 24. This expression or mathematical statement is totally different from what we did in our earlier episodes. How it is different? Because there is no mathematical equation is there. Equality sign is not there. We need to prove that this expression is divisible by 24. There is slight different approach to solve these type of questions, but basic steps will remain same. What are the basic steps? First we will assume that this given statement is Pn. We name it, we define it by Pn. Now we check the divisibility, we check the truth for P1. P1 means for n is equal to 1. After replacing this n by 1, what do we get? 2 into 7, 3 into 5 minus 5, we get 24, which is obviously divisible by 24. So we can easily say that P1 is true. Once P1 is true, we can go further in assuming that Pk is true. Because to prove it further, we need to assume that it is true. So what is Pk? Pk is the statement, given statement in the form of k. Wherever there is n, we will replace it by k. So this statement comes in form of k. Now this is equal to 24q. What is 24q? Because we just said, we assumed that Pk is true. Pk is true means it is divisible by, this expression is divisible by 24. If it is divisible by 24, it has to be some multiple of 24, some positive multiple of, where q is some natural number, 24. Now we move further, we wish to prove that Pk plus 1 is true whenever Pk is true. Now what is Pk plus 1? In Pk plus 1, we will just replace n by k plus 1. And we need to show that this expression is divisible by 24. We will solve it by law of exponents by opening these powers. How? By taking left hand side. 2 into 7 power k plus 1 will split into 2 parts, 7 power k into 7 power 1. Similarly, 5 to power k plus 1 will also split into 5 power k into 5 power 1. And after writing this whole expression, this is very important step to note. We have divided this expression into 2 parts. How 2 parts? One part is this, another part is this. We are going to make change or add something to this part. We will not touch this part. What we will add or subtract whenever we make some addition to some expression, we need to subtract the same term also. Similarly, here what we have done is we have taken 7 outside. What we are left with 2.7 power k. In 2.7 power k, if we add or subtract the same quantity, it is not going to make any difference. Same way, we have subtracted 5 and added 5 without making any difference. But why we did so? This is the main difference for these type of questions. What we want to bring is, we want to make this expression something similar to pk. We want to make this expression similar to pk. Here we needed 2 into 7 power k plus this term minus 5. So, to get this term, we have added and subtracted these two. Same way, we needed minus 5, we have to add 5 also to make it similar to pk, and we have not touched these expression, so this will remain same. Before moving to next step, we have rewritten this statement which is to be proved. Next, this expression we have added and subtracted simultaneously so that our expression does not change, and same way 5 subtracted and added, and this expression remains same. Now, which part we needed for pk? This much part, right? And this was, in the previous slide, we proved that pk is equal to 24q. This 24q we are using in place of this much expression, and rest of the terms as it is, as you can see. And from where we got this 15.5 power k? This 3 and 5 get multiplied, 15 5 power k minus 1. Now, we need to multiply this 7 with this entire bracket 1 by 1, 7 into 24q, 7 into 3, 21, 5 power k, 7 into 5, 35, and rest of the terms as it is. Now, these highlighted terms, 2 highlighted terms, why we have highlighted this? Because these are like terms with the same 5 power k expression in them. These can be solved further. These 2 terms will reduce to this term, which is minus 6 into 5 power k. Rest of the terms we have kept as it is. Now, moving on further, 35 minus 5 will make it 30, rest of the terms as it is. Moving further, from these 2 terms, what we take? We can take common, 6 can be taken common, minus 6 we have taken. Here we are left with 5 power k minus, this 1 plus sign is extra here, minus 5 inside, because minus sign is taken outside. That is why negative sign will be left inside. Now, this is multiple of 4. How? Because whatever is the value of k, as we said earlier that k is some positive integer or natural number. If we replace k by 1, 5 power 1 minus 5, that is 0, and 0 can be divisible by any number. And if we replace it by 2, that is 25, 25 minus 5 is 20, and 20 is also divided by 4. So, we can say whatever is the value of k it will be divisible by 4. If it is divisible by 4, this expression can be replaced by multiple of 4. So, 4p where p is some positive number. Now, further multiplying it, this gives us 24p. From these two expressions, we can take 24 common. After taking 24 common, we are left with 7q here and p here. Now, since both of these are positive numbers and we can take this is a natural number, and in place of this 7q minus p, we can replace it by r. So, this becomes 24r, which is multiple of 24. So, r truth of pk plus 1 is established. Hence, by PMI, Pn is true whenever n belongs to natural number. Now, moving to next question. Question number 22 of exercise 4.1. This is very similar question to what we did now. This is the expression given. We need to show it that this is divisible by 8. As usual, we will consider this as a statement Pn. After considering it Pn, we will verify it for P1. For P1, after replacing n by 1, we can find out this is 3 to power 4 minus 17, which is 64, and 64 is divisible by 8. So, P1 is true. Now, what we need to do is we need to assume that Pk is true. And what is Pk? Pk, writing the statement Pk by replacing n by k. This is the statement, and we will consider this statement to be equation number 1. After taking it as equation number 1, because we will using it further, we shall show it for Pk plus 1. This is the statement. We have written it as Pk 8m because we have proved that this is divisible by 8. Now, moving on to Pk plus 1, we need to show that this is true whenever Pk is true. Mathematically, we can write Pk plus 1 as replacing n by k plus 1, and we need to show that this is divisible by 8. Means we need to show this is some multiple of 8, some multiple where p is some positive number. This is the statement of Pk plus 1. We have rewritten the statement to be proved. This side we need to show that this is some multiple of 8. Now, consider left hand side, this side only, and after solving this 2k plus 2, this becomes 2k plus 4 minus 8k minus 8 minus 9. Now, this gives, we have split this 4 into 2 plus 2, rest of the terms are same. And why we have split? We want to make this expression separate, 3 to power 2k plus 2 and 3 to power 2 separately, and adding these two terms. And the next is, this is 9 taken here, and what this expression is? This is we have obtained from the previous term where we had written in the equation number 1 that it is equal to 8m. After taking them on the one side, we get the expression for 3 to power 2k plus 2 is 8m plus 8k plus 9 and minus 8k minus 17. We have multiplied each term by 9, we get this term, and solving this, we can easily take 8 outside because all these terms are multiple of 8. After taking 8 common, we are left with this. Now, since these all terms are positive numbers, we can replace them by some number p. So, this becomes 8p. 8p means this expression is divisible by 8, and hence it is proved that pk plus 1 is true. Since it is divisible by 8, Pk plus 1 is true whenever Pk is true. So, therefore, Pn is true for all n belonging to natural number. Now, we move on to next question, which is question number 18 of exercise 4.1. Prove using principle of mathematical induction 1 plus 2 plus 3 plus 4 plus n dash dash n is less than 1 by 8 into 2 n plus 1 to the power 2. How this question is different from earlier one? Because this question involves inequality. No equal sign, no divisibility sign, this involves inequality. And approach to solve these kind of questions is also slightly different. But first step is same, we assume or define the statement as Pn, then we establish its truth for P1. For P1 we take first term on the left hand side and replace n by 1 on the right hand side, and we see that 1 is less than 9 by 8. So, P1 is, truth of P1 is established, P1 is true, and now we need to assume that Pk is true if we want to prove it further. For what is Pk? We just replace n by k and this expression goes like this. We need to show, we have assumed that this is equal. So, this is equation number 1. Now, we need to show that Pk plus 1 is true whenever Pk is true. We will write Pk plus 1 as Pk plus 1, just replacing the term k by k plus 1. Here we have written one previous term to k plus 1 because this was k plus 1th term and this is kth term. And same way here we will replace k by k plus 1. Now, as you can see in this expression, this part is till kth part. We have already shown that this is less than 1 by 8 to k plus 1 to power 2. Now, moving on to next, we have rewritten the statement for Pk plus 1 and we need to establish that this is the expression we need. We have taken this as equation 2. Let us write equation 1 again because we need to use it. This is the equation 1 which we proved or assumed for Pk. We will be using this, adding k plus 1 to both sides of equation 1. Now, here is the trick. In these kind of questions where inequality is involved, we need to make the statement equal to Pk plus 1. In equation 1, which term will be adding so that it becomes the left hand side of equation 2. In these two expressions, the difference is of k plus 1. So, if we will add k plus 1 to left hand side, we need to add it to right hand side also simultaneously. That is why we have added k plus 1 to equation number 1 on left side as well as on the right side. Now, after opening this expression a plus b whole square by using this identity, this gives us this relation 4k square plus 2k into 2 plus 1 plus k plus 1. Now, taking 8 as LCM, this will be multiplied by this expression and this expression becomes like this. Further solving it, this gives us this whole thing is less than 4k square plus 12k plus 9, and this is the formula for 2k plus 3 whole square because we have used this identity here which is equal to a plus b whole square. So, this gives us 2k plus 3 whole square and which is equal to right hand side what we wanted to prove. Hence, Pn is true for all n belonging to n. Now, we move for next question. The next question is an example 7 of chapter 4, which is a similar question involving inequalities. Here 1 square plus 2 square plus 3 square plus dash 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 n square is greater than n cube upon 3, which is sum of squares of natural numbers till n terms. The same method, same approach. First step, we will consider this definition as Pn. This is Pn. Now we will establish its truth for n is equal to 1. Putting n is equal to 1 on left side means we will be taking only first term and that is 1 square. On right side we will substitute n by 1, which is 1 is greater than 1 by 3. Therefore, we can say that P1 is true. Now we assume that Pk is true whenever k is some positive integer. What is Pk? We will just replace n by k and this expression becomes 1 square plus 2 square plus 3 square plus k square is greater than k cube upon 3 for all k belonging to natural numbers. And we will take this equation as equation number 1 to use it further. Now we need to prove that pk plus 1 is true whenever pk is true. What is pk plus 1? Again the same similar step, we need to replace n by k plus 1. Here we have replaced n by k plus 1. From where this k square has come? Because this is just the previous term. We have taken the sum till k plus 1th term and just previous term can always be written. So, we have written here plus k square. Now, considering the right and left both side in these type of questions, as we discussed in the previous question, we need to add the term which help the first equation to make it like a second equation. So, only difference was k plus 1 square, that we will add to both the sides, left hand side as well as on the right hand side. Same expression will be added. Now, solving left hand side, you can see here we will open k plus 1 whole square and this k plus 1 whole square has been opened, 3 taken LCM multiplied by k and we get this expression k cube plus 3k square plus 6k plus 3, which is equal to, now what we have done is we have split this 6k in two parts, 3k plus 3k, and we have splitted this 3 into 1 plus 2, so that it becomes an expression of k plus 1 cube till these terms. If you use these terms, these 4 terms, leaving these 2 circle terms will make k plus 1 whole cube plus 3k, the left one, plus 2, and that is greater than k plus 1 whole cube, obviously, because if we take this much part, here something is more. On the left hand side, 3k plus 2 is more than this side. So, therefore, we can definitely say that expression on the left hand side is greater than expression on the right hand side. So, pk plus 1 is true whenever pk is true, and whenever pk is true, pk plus 1 is true, by PMI we can say that Pn is true for all n belonging to natural numbers. And that is all for module 3. Here we today covered more examples on principle of mathematical induction involving inequalities and divisibility problems.